Okay, welcome to 5-3 Supplementary Notes. Hopefully this will make a lot more sense if we kind of work through some basic examples first. So, there we go. So this is about kind of how you think about combining random variables. And remember, when you have a random variable, like the number of hours an FHS upperclassman spends doing homework per night, the random variable doesn't have a value until there's an outcome from a random event. So the random event here would be we draw a random FHS upperclassman, and then we ask them, how many hours do you spend doing homework? And so then X has a value, and maybe they spend 0 hours, maybe it's 1, maybe it's 2. So if we did this over and over and over again, we would get a distribution, and that distribution would have a mean value, which is what we call the expected value. It would have a spread, and you can measure the spread with either variance or standard deviation. So we're going to sort of like think about how you calculate those things for one variable, but then the big question is, what happens if we have two different variables? They each represent a distribution. Sort of how do you think about combining those distributions? All right, so we've got the situation. Of course, people could spend any number of minutes studying, but for today's purposes, we're going to treat it as a discrete variable. So we're going to say there's only 3 possible answers: 0 hour, 1 hour, or 2 hours. So let's assume that we've got these probabilities. Random upperclassman has 5% chance of not studying at all, 75% chance of studying for an hour, 20% chance of studying for 2 hours. So the expected value equation looks like this, and I was encouraging you to kind of memorize what the little bits mean. So this sigma means add all the things up. And what we're adding up are these pairs of multiplied numbers. So you're taking, you're going to list all the possible outcome values, and for each outcome value, you're going to multiply that outcome value by the corresponding probability. So we'll multiply 0 hours times 5% and add that to these two and add that to those two. So here's what that would look like once you're done. So here I've just added up all of the multiplied pairs. See that here. And I get 1.15. And I think it's a good idea always to try and attach units to whatever it is you've calculated. So on average, the average amount of time studying is 1.25 hours. Oh, not quite a quarter. 1.15 hours. Okay, so what about variance and standard deviation? So both of these are measures of spread. And here's how they're related. Standard deviation is just the square root of variance. Or you might like to think about it this way. Standard deviation squared tells you the variance. So if you're wondering, why bother having 2 different measures for spread, the answer is that they're useful for different things. And I'll tell you more about that on the back side of the sheet of paper. For now, let's look at sort of the equation. So this equation, if you can sort of get past all the crazy symbols and you can compare expected value to variance, they're very similar. In both cases, I'm adding up all the things. Here, I'm multiplying each outcome value by its probability. Here, I'm multiplying this whole blobby thing times its probability. What's this blobby thing? This blobby thing is the difference between an outcome value and the average value, and then I square it. So I think it's an organized way to do this would be to add another column to the table. So this is the same table as here, except now I know that I want to be multiplying this difference from the mean value squared times each probability. So I'm going to write down what's the difference from the mean value squared. So here I've got 0 hours is my outcome value. My mean value I calculated right here just a second ago was 1.15. So I'm going to find that difference squared. For 1 hour, I've got 1 minus 1.15 squared. Here I've got 2 hours, 2 minus 1.15 squared. So just like up here, I'm going to multiply this by that and add it to this times this and add it to this times this. So you're multiplying pairs and adding them. Here's the result you get. So I'm getting 0.2275. Okay, what are the units here? So each of these things that I'm calculating is a difference from the mean, and the units of each of these measurements are hours. So 0 hours minus 1.15 hours. So when I square them, it ends up being squared hours. So the unit here is actually hours squared, and if you're thinking that doesn't make any sense at all, you are thinking the right thing. That's why we usually don't report variance as a measure of spread, because the units are difficult for humans to interpret. There's a different reason why variance is useful, which we'll do on the backside. But anyway, so that's how you calculate variance. Standard deviation is just the square root of the variance. So you take this same calculation and you take its square root. So square root of 0.2275 hours squared, and we get 0.47697 hours, because if we're taking the square root of hours squared, the units are now hours. And that's a unit that makes sense as a unit for measuring the spread of our data in our distribution. All right, so let's think about what's the conceptual difference between finding the expected value of 2x versus the expected value of x plus x. And actually, I'm going to add subscripts here, x1 and x2, because I want these to represent two different random events. This is the random event where I choose a student at random, ask them how long they study. Here, I'm going to choose another student at random and ask them how long they study. So because there's a different random event, I'm giving them different names. The probability distribution for each of these events is the same. It's still that one that was in the table. But I'm actually sort of choosing two different students. All right, so let's think about this conceptually. So one way of thinking about this is I'm taking x, which is number of hours studied, and I'm doubling it before I find the expected value. So that would be like, oh my gosh, it's almost time for finals. Everybody is going to double their study time. So this is the same probabilities as the top of the table, but now the person who is studying for 0 hours is doubling their study time. Oh, still 0. The person spending 1 hour is going to double their study time. 2 hours, they're going to double their study time. So I'm pretending all students are doubling their study time. So if I find the expected value, I could just calculate it, the same way that I did at the top. Sorry for the the poor writing. So I apply the formula and I get 2.3 hours. And something that you might notice is the original expected study time was 1.15. And if I take that and I multiply it by 2, that gives me the same thing, 2.3. So conceptually, this 2 on the inside is saying, let's double all of the outcome values and then find the expected value. But we've seen from this example anyway that it seems to be the case that you'll get the same answer if you find the expected value first and then you double it. Okay, what about this side? You might be nervous that my table is so long. So if I'm interested in the expected study time of 2 randomly drawn students, so like I pick a student at random, I pick another student at random, it might be the same student, and then I ask them each, what was your study time? And I add them together. I'm trying to find the expected value of all of those possible sums for 2 students' expected study time. So if you were going to find the expected value the long way, we've got a lot more outcomes now, because we're not going to do the expected value until we draw 2 students and ask them both. So here's all the possible outcomes. Student 1 could have 0 hours, student 2 could have 0 hours. Student 1 could have 0 hours, student 2 could have 1 hour. Student 1 could have 0 hours, student 2 could have 2 hours. Student 1 could have 1 hour, and then 0 hours, 1 and then 1, 1 and then 2, 2 and then 0, 2 and then 1, 2 and then 2. So this is sort of every single possible combination of study times for my 2 students. So here my outcome value is 0, 1, 2, 1, 2, 3, 2, 3, 4. Okay, so a lot of possible outcomes for my sum. What are their probabilities? We're assuming that the draw is an independent event. So what's the probability I'd draw a 0 studying student and a 0 studying student? It would be 0.05 squared. What about a 0 hour student and a 1 hour student? So a 0 hour student is 0.05, and then I'll multiply that by the probability of choosing a 1 hour studying student, which was 75. So you could fill in all the probabilities, And then if you were going to calculate the expected value, you'd be multiplying all these pairs and adding them up. And that seems like a lot of work. So that's not actually how you calculate the expected value of this. But what's important, the reason I went through this is because I want you to understand conceptually when you see a symbol that looks like this, that's what it's talking about. It's talking about there's two random events. You do each random event, and each of these have a value, and you add together the values. And now you're trying to list all the different possible outcomes of the sum of those values. And so we're finding the expected value of all of those sums. Okay, so let's flip over to the back. So we don't calculate expected value this way because that would be a lot of work, and there are kind of easier, shorter ways of doing it. So up here, it suggests immediately an easier, shorter way of doing it. This says that the expected value of the sum of two events is the same as if you find the expected value of the first event, as if the second one never happened, the expected value of the second event, as if the first never happened, and then add them together. So on the front page, if we wanted to sort of look and see how that would play out, the expected value of the first student's study time is 1.15 hours. The expected value of the second student's study time is also 1.15 hours. You can add those together, and you'd get 2.3 hours as the expected value of both of them, which in this particular example is the same as the expected value if one student was doubling their time. But that was just a coincidence. So again, I want to focus on the conceptual difference. Here we've got only one variable, so there's only one random event. It's one student. And we're saying what's the expected time if they double their study time. Here we're saying what's the expected study time if there are two students and we add together the times they studied. So we're asking very different questions here, even though we're getting the same numerical answer. Okay, so let's look at what all these simplification rules look like. So over here we're saying the expected value of 3 times a variable is the same as 3 times the expected value of that variable. And that's just like what we did on the other page. In Unit 1, we had actually a good way of thinking about this. It's like if you have a distribution and you multiply all the values in your distribution by 3, that's like you're going to stretch your distribution way out. So if this was at, let's say this was a mean value of 2, if I'm multiplying all my values by 3, the mean value is going to end up here at 6 because the mean value also multiplies by 3. And you did that before, and I'm just pointing out it's the same thing. Here for standard deviation as well, if your standard deviation is a measure of the spread. So if I'm taking all of my values and I'm tripling them, I am also tripling my spread. So here, if the standard deviation was 1, and I triple all my values, the standard deviation is going to also triple to be 3. And so this equation just says that same thing. Standard deviation of tripled values is 3 times my original standard deviation. So the one that's new is about variance. So if I have the variance of my tripled data, that's not 3 times my old variance, it's 9 times my old variance. And the reason why is because variance is standard deviation squared. Okay, so let's jump on over to this other side now, where we'll get a chance to use these in problems in just a second. So this is all about, still we just have one variable and we're multiplying by a constant. Here it's like what happens if we're combining 2 different random variables. So we already said that if I've got 2 different random variables and I want to know the expected value of the sum, it's like you find them separately and add them. It turns out that is also true for the variance. So this particular measure of spread, I can figure out what's the spread of my first distribution, what's the spread of my second distribution, and add them. And that's the same as the spread of the combined distributions. It's very important, so like this is definitely a thing where you might mess it up on the test. That is not true for standard deviation. And that's why we have 2 measures of spread, variance and standard deviation. I said on the first page that variance has units that don't really make sense, like my spread is in hours squared. That doesn't really make sense. So when you're reporting the spread for human beings to read, you usually report standard deviation because that's easier to interpret. But variance has this really nice property where we can take a combination of two things and figure them out separately. And that lets us simplify our problems a lot. And so that's why we even have variance. All right, so let's use this for some problems. What if everyone spends 50% longer studying and also adds 1 additional hour to their study time? So how would we write that down in terms of expected value? So 50% longer study time means they're studying 1.5 times as long. So I'm finding the expected value of 1.5x was my original random variable. And we're adding an additional 1 hour beyond that. Okay, so here I see expected value of two things, expected value of this thing and this thing. So let's treat each of these as a random variable and apply this equation where I can find expected value of each of them separately. So now I've got expected value of 1.5x plus the expected value of 1. And you might think, whoa, we haven't seen that before. Hold your horses. We'll do that in just a second. So now let's simplify this one. Expected value of 1.5x sort of fits this. I'm multiplying x by a constant. So this should be the same, this should be the same as 1.5 times the expected value for x. Okay, so let's start to simplify now. I had this sort of more complicated expression. I used these rules to break it apart into pieces. I know from before that my expected study time was 1.15 hours. Let's think about this, the expected value of 1. Well, usually what you have on the inside here is a random variable, which has a distribution. And so expected value is about the mean value of the distribution. Here, 1 is just a constant. It doesn't have a distribution of different values. So if I just have one thing and I want to know, like, over the long run, what's the most likely, what's the average value I'm going to get, the answer is just 1, because that's the only value I could ever get. So the expected value of a constant is really just the constant, because there is no variety, there is no distribution of values there. So you use your calculator, and we've got 2.725 hours. All right, let's do variance. What if I want to know what's the spread of the study times if this is all of the outcomes that might happen? So again, let's say variance of 1.5x plus 1, and let's use our rules again. So just like on this other side, I've got the variance of two things, so I can use this equation and split them apart. So that should be equal to the variance of 1.5x plus the variance of 1. Here I can use the rule where I can pull this to the outside, except when I pull it to the outside, I've got to square it. So I've got 1.5 squared times the variance of x plus the variance of 1. Okay, so how are we going to make sense of each of these things? My original variance, I got to look up from the front page because I forget. All right, so there it was. Just like over here, like what is the expected value of 1? I might ask what's the variance of 1? And again, this is not a random variable. There's not a distribution of possible things where there's a spread. 1 is just a single number. So if you ask yourself, what's the spread for a single number? It's like there is no spread. So the spread is 0. So that's one way of interpreting it. The spread of a single number is just 0 because it's not a distribution. A different way of imagining it is this. Let's say I've got, so 1.5x is going to give me a distribution. What happens if I add 1? That's like taking my distribution and shifting it right by 1. Well, if I'm interested in what happens to the spread of my distribution if I shift it right by 1, the answer is that everything is getting shifted by the same amount. So the spread doesn't actually change at all. And so that's another reason why you can ignore adding constant values when you're interested in measures of spread, either variance or standard deviation. Okay, so we've got our variance. Let's do the last one. Let's pretend I'd asked you what's the standard deviation of 1.5x plus 1. Here, I can't apply this equation because this is not an equation. I can't say this is the standard deviation of 1.5x plus the standard deviation of 1. So one thing I could do would be I could say, first, let's find the variance of this thing. So I'd go through all the steps to find the variance. And then at the very end, I'd say, all right, so standard deviation is just the square root of the variance. So that's one thing I can do. Whenever you're asked to find standard deviation, you should always think, maybe I'll find the variance first, and then take the square root. And that would work. In this particular example, a different thing you could do is you could say, oh, hey, I know that adding 1 just shifts my distribution, and that shouldn't change measures of spread. So standard deviation of this should be the same as standard deviation of 1.5x. And then you can say, all right, and so this should be the same as this equation up here, which is just 1.5 times my original standard deviation. And these should end up being the same value. All right, let's do the last set of examples. So my original table on the front page was about study habits of upperclassmen. What happens if I also make a table for the expected outcomes of lowerclassmen? So a lot more lowerclassmen don't study at all. A lot fewer of them study for 2 hours a night. And again, I just made all this up. And using the techniques from the front page, I've already calculated for us. So let's say this table corresponds to the random variable y. The table on the front side corresponds to x. So the expected number of hours for underclassmen to study is this. The spread is this. Standard deviation is this. Okay, so let's apply our rules now for expected value, variance, and standard deviation. So expected value of x plus y. Oh, let's think about what does this mean, actually. So what this means is if I'm going to randomly pick an upperclassman and a lowerclassman, ask each one of them, how long did you study, and then add those two numbers together, you can imagine that if I did that over and over and over again, I would have a distribution of possible values. And those values might range between 0, and they would go all the way up to 4 as the maximum, because I might randomly choose an upperclassman who studied for 2 hours, and a lowerclassman who studied for 2 hours. Okay, so that's what this means. I'm imagining a distribution where I've chosen 2 people, asked them their study times, and added them together. So what's the expected value of that distribution? Well, from the rules above, we've got it that it should just be expected value x plus expected value y, and we can just read those from the other places. So this we calculated on the first page. This I told you what it was right here. And so the answer would be 1 3/4 hours. All right, let's do variance. So if I want to find the variance of x plus y, we have this nice property where that's also something where you can just break them apart. So variance x plus variance y. And now we can look them up. And there's the answer. All right, standard deviation, x plus y. So this is one where you can't split them into parts. So think, what did I advise just a minute ago whenever you're trying to find standard deviation of something? You think, okay, let's find the variance of that thing instead. Let's find the variance of x plus y. Because you know that if you have the variance, you can just take the square root to find the standard deviation. Okay, so if I'm going to find the variance, then you solve it, in this exact way. If you're finding the variance, you split them into parts, you find each part separately, you add them up. And so now that we know that the variance is 0.6675 hours squared, to find the standard deviation, I'll just take the square root of the variance. So standard deviation of the sum of the variables is the root 0.6675, which is what? There we go, 0.817 hours. All right, so I think now if you go back and you try those same Animal Crossing problems, hopefully it will make a lot more sense to you. Let's just sort of recap where we came from. So first, you should always be clear in your head what the symbols mean. So ask yourself, what is this really asking about? What is this really asking about? And think the same questions that I asked you to think about before. For a random variable, ask, what is the actual random event? What's the random thing that needs to happen before you know what value this is? And then you should ask, what's the range of all the possible outcomes for that random event? And those outcomes have values, and maybe the values are dollar amounts, or maybe they're numbers of darts, or maybe they're hours of studying. And then you want to ask, what's the probability of each of those outcome values? And that's the set of things you need to know. And so you can always write it down in a table, and I kind of like the idea that if you're not sure what to do, write a table where you ask yourself, what are all the outcome values, what are their probabilities, and now you can start filling things in. When you read a problem, there will probably be some random variable, but then they might try and make it more complicated for you. Maybe it's more complicated because it's hard to figure out what all the outcomes are. Maybe it's more complicated because they're saying, all right, let's take the random variable, which is study time, but now let's say that we're going to multiply it by something and maybe add and subtract some stuff. Maybe we're going to add it to another random variable. And so you'd write your expected value or your variance or your standard deviation of some mathematical expression on the inside here. And then you use these equations to take the complicated thing and break it into smaller pieces, and then you evaluate each of the pieces separately. All right, I hope this felt better. To feel really good, go ahead and retry those same problems.